Now we rotate a list to the left by k places at once. With k equal to 3, the first 3 elements move to the back and everyone else shifts forward. Doing this one step at a time k times is wasteful. There is a beautiful trick using reversals that does it in one sweep. Here is the elegant part. First we reverse just the first k elements, then we reverse the rest of the list. At this point, both halves are individually flipped. Finally, we reverse the entire list. The 2 flips cancel out inside each block, but swap the 2 blocks into their rotated positions. So 3 reversals give us a left rotation by k, and we only need k modulo n to keep it in range. The helper reverse swaps elements from the 2 ends inward until they meet. In rotate left, we first take k modulo n so a big K wraps correctly. Then we reverse the first k, reverse the rest, and reverse the whole thing, which lands every element in its rotated spot. Let's build the reversal trick and rotate a couple lists. A small helper that reverses the slice between 2 indices by swapping from both ends inward. We take k modulo n first, so rotating by more than the length still behaves correctly. Reverse the first part, reverse the rest, then reverse everything, and the rotation is done. Now let's test it and hit run. Rotating 7 elements left by 3 brings 4 to the front, with 1, 2, 3 tucked at the back. The second list rotates by 2 the same way, all from 3 simple reversals. First we bring k into range with k modulo n. Then 3 reversals in order, the first k, the rest, and the whole list, and the array is rotated left by k. Every element is touched by at most 2 of the reversals, a constant amount of work each, so the total is order n time. The swaps happen in place, so order 1 extra space. Always reduce k with k modulo n first, otherwise a large k pushes your indices out of range. Watch the reversal boundaries, they are inclusive, so the first block ends at k minus 1. Remember, left and right rotations split the array at different points.